The method of joints is one of the two ways we can find the forces in the individual members of a truss. The other is the method of sections, which we'll look at in a different video. The method of joints revolves on a single concept, fundamental concept, which is that if the truss is in equilibrium, then each of its joints are in equilibrium too. And we're going to follow a two-step process to solve these. First, we'll find the reaction forces and moments, and then we will apply the method of joints to solve each joint as a separate problem. So, step one, we will find the reaction forces and reaction moments. So let's just do this following the standard 4 steps for solving any rigid body problem. Imagine we have a rigid body truss that looks like this, pin joint on one end, a roller on the other, and an applied force F going like this to the side. The first thing we can do is label our points. I'm going to call that one A, B, and C. And if we were to draw a free body diagram, we would remove the supports and instead give this its reactions. So A has a vertical reaction and a horizontal reaction, and C has a vertical. So if we define X and Y like so, we can call this a Y, this one a X, and this one CY. Sum of forces, sum of moments, we can solve that to find the reaction forces AX, AY, and CY. So those become values that we now know as we move forward with our analysis. So the second step is to actually apply the method of joints, which is where we're going to solve each joint as a separate particle problem. So those are going to follow the same steps. We're going to do a free body diagram at each joint, then we're going to do a force balance at each joint, and then work out the geometry, and finally the algebra to solve this thing. So let's start by doing a free body diagram at each joint. Actually, I'm going to make a new page here so that we have more room. So I'll write this farther up. So first thing we'll do is the free body diagram. And so at joint A, we have AY and AX already in the picture. And what we want to do is we want to add forces to represent the forces that are either in tension or compression in the elements. So we have a force running in the vertical element that is AB for this element here, truss member AB. And we have a force that goes horizontally, which we can call AC to represent the tension or the compression that's happening in AC. We'll repeat this at each of the joints. So joint B gets a free body diagram as well. I'm going to draw it with a different color, make it a little easier to differentiate here. So joint B is also going to get a free body diagram. And at joint B, we want to make sure that anything that happened in a different diagram is equal and opposite. So for example, the force AB runs vertically from the free body diagram in A, so it'll run down vertically this time. And we have the force, oops, that's going to be in the way. Put that over here. AB, AB. F still acts horizontally at joint B. And lastly, we have a force for the diagonal member, which we will call BC. You'll notice that I drew this one pointing in. We are drawing the free body diagram of the pins in each of these joints. And so we're actually drawing the forces that are acting on the pins, which are equal and opposite to what's happening in the element. What's that mean? Well, if the element is in tension, if we're pulling on the bar, then the effect of that on the joint, the pin, is that the pin gets pulled the other direction. And so when you see arrows going into the joint like this AY, this is assumed to be tension because it's well, not that one because that's a reaction force, but AB here we've assumed to be tension because it's pulling on the pin. BC I drew pointing into the pin because if we were to press on the member, then a force would be pushing on the pin as well, equal and opposite, right? So this is BC, and it is assumed to be in compression. We have a third free body diagram to draw at joint C. At joint C, we have the reaction force CY. We have a horizontal force AC, which we drew to the right coming out of joint A, so we'll draw it to the left. And this, equal and opposite that way. And again, that means tension because it's pulling on the pin. BC we drew in compression, and so again we've flipped the direction of BC because it's in compression, it points into the pin. So there's our free body diagrams. Just like any other statics problem, from here we would do force balances for each joint. In a different color here, force balances. And so now what we'll do is we'll do a force balance at each joint. So joint A here in the horizontal direction, again we already wrote a coordinate system here, x, so sum of fx needs to equal 0. It's going to equal minus ax plus ac. Some forces in the vertical direction fy needs to equal 0. We have ay going up and we have ab going up. By the way, the fact that those are both positive tells you one of them's actually drawn the wrong direction because we need that to add to 0. Do this again at joint B. Change colors here maybe. Whatever. Joint B here. Sum of forces in the x direction at joint B. We've got F in the positive direction, and we've got the x component of BC in the negative direction. Sum forces in the vertical, the y, and that's equal to 0. And we get negative AB because it's pointing downward, and the positive BCY because it goes up, and that equals 0. And then lastly at joint C, we'll get one more here. Slide this up just a little bit. At joint C, we have the sum of forces in the x direction, which look like minus AC plus the x component of BC. And in the y direction, we get plus CY minus the y component of BC. So there's our force balances. And from there, just like in any problem, we want to do some geometry. So our next step is to work out any geometry that we might need. In this case, the only thing that needs to be broken into components is the force BC. So if we call this angle here theta, we can write that BCX would be equal to BC cosine theta, and BCY would be equal to BC sine theta. And now we can sub that into our force balances and move on to the final step, which is actually going to be solving the problem. So, geometry's done. Now we're looking at doing some algebra. Right, what I want you to notice is if we do an audit here, once we sub that in, right, anywhere that you see a BC, we're going to sub that in. And so now where we end up is we have the first equation, sum of fx equals 0 is minus ax plus ac, ac. Sum of fy equals 0 for the first node. Looks like ay plus ab. Just copying these all down here real quick. When we go to joint B, sum of fx equals 0, we get f minus, and now we're going to make a substitution, so this will be BC cosine theta. and in the vertical we get minus AB plus BC sine theta. And then lastly, at the last joint, we get sum of fx equals 0. That's going to be minus AC plus, and now we get to do another substitution, BC cosine theta. And slide this just a little bit further up. Sum of fx equals 0 equals cy minus, and bcy gets a substitution, BC sine theta. So what did I do? I wrote the force balance at each joint. I did the geometry needed to break it into components, and now here we are. So let's do a quick audit, okay? By solving the external reactions back in step 1, we know AX, we know AY, we were given F, see where else, and we know CY. So our unknowns are AC, AB, BC, and that's it. We know our three unknowns are AC, AB, and BC. And we actually have 6 equations here. So turns out we have extras, right? And we can do some algebra here and we can find things. For example, we could use this equation here to discover that BC is equal to F over the cosine of theta. We could sub that in places to find things like this one now could be used to find AB as BC sine theta. And lastly, we could use this equation now to find AC as BC cosine theta. And so that's how these are always going to work. So just to recap real quick here, we started out by drawing free body diagrams at each of the nodes. And the trickiest part is if you assume tension, then it's going to pull on the pin. And if you assume compression, it's going to push on the pin. So BC was assumed to be compression, AB was assumed to be tension. We write a force balance at each of the nodes. So we end up with 2 force balances for each node if this is a 2D problem. And then from there we do the geometry needed to break anything into its components. Lastly, we have now a system of equations where we have 2 equations for each of the nodes. And you'll see that we can now write the sum of forces like so, and we can start looking to see which ones we could solve based on how many unknowns are sitting in them, and eventually work out all of the unknown forces in all of the members. By the way, you don't necessarily have to write out the equations for every single node, and as you practice, you'll start to see how you can choose which nodes to write it at and which ones you can kind of skip to save yourself some time.